So I'm going to share what I had indicated was a less traditional domain, but as we've heard today, several things about CO2 applications. This is a project that we've implemented within the past few years, but we've really ramped up the HPC in the past year. And so, oops, I guess I'm looking at the same slide. Okay, so TotalEnergies developed an ambitious CCS program, or CCUS, and for those of you who aren't familiar, CCUS is Carbon Capture, Utilization, and Storage. I'm going to focus this presentation specifically on the capture portion. Our project is called Adsorptive CO2 Removal from Dilute Sources. So what do I mean by dilute source? Basically any carbon dioxide concentration below 15% and down as far as 4% concentration. And two industry examples of this would be natural gas combustion, or NGC, or DAC, which is direct air capture, and that could come from several energy sources. So our challenge is to drive down the high costs as a company from around $600 per ton of CO2 captured, with a goal of $200 per ton in the next few years and $100 per ton in the longer term. Materials and processes are the two big offenders, with the adsorbent and the contactor accounting for 80% of the CapEx, and the steam regeneration process accounts for about 30% of the OpEx. So those are the two items we're going after in this project. And we're using HPC to accelerate the discovery of these novel materials, specifically metal organic frameworks, which Jake's going to talk more about. And we're doing atomistic simulations, so we're running tens of thousands to hundreds of thousands of DFTs, as well as using data-driven methods to using GANs to focus our design space a little better, and also use them to develop new metal organic frameworks. So we're leveraging our in-house HPC competence and facilities, as well as our best-in-class partners, such as University of Ottawa and Argonne National Lab. And specifically, part of the work for this part of the project was funded through the DOE's HPC for Energy Innovation program. So with that, I will hand the floor over to my colleague, Jake.
Great. Okay, great. So yeah, as Donnie said, I'm going to talk a little bit more about the problem that we're trying to solve. And so giving a little bit of context into the problem, specifically CO2 capture using metal organic frameworks. And this isn't working. All right. There we go. Other way. Okay, so yeah, just a bit of an introduction to the research group. So I'm with Dr. Tom Wu's research group at the University of Ottawa. And so this is our group here. We've got a few links if you're interested in checking out some of our work. And yeah, I thought I'd just say a couple of interesting facts about Canada, or Ottawa rather. Canada's capital city, about quarter of the population there speaks French in Ottawa. And yeah, I'm very happy to be here in the warm weather. So I'm going the wrong way again. Okay, so what is our research objective in the Dr. Wu's research group? So mainly, as Donnie already said, we use atomistic simulation and machine learning in order to investigate properties of different materials. And so specifically the materials we're interested in are these metal organic frameworks. And our goal is to specifically discover solid sorbent materials for CO2 capture. So what we look at is a lot of the time that we spend is looking at these atomistic simulations, just shown sort of in this picture here. So from these simulations, what we can do is we can get some CO2 capture properties of different materials. And further down in the project, from other collaborators, so we don't look specifically at this, but there is work on these advanced process simulations which are accelerated using machine learning. So we're not only looking at the properties of the materials, but the actual performance that the materials would have in a real capture process. Okay, so what is a metal organic framework? So again, this is going to be a very basic introduction into this. So these are porous solid materials. So you can think of it like it looks just like a powder. This solid material is composed of metal nodes and carbon-containing linkers. And so what we can do is we can just come up with all kinds of different organic linkers like are shown here, and all kinds of different metals combined into different nodes. So here we're looking at metals like nickel, copper, and zinc, and so on. And then we can combine them into 3D porous networks. And porous is important, right? Because these materials will be used in order to capture or separate carbon, CO2 from flue gas. And so why are we particularly interested in MOFs for CO2 capture? Well, they've attracted a lot of attention. I'm just going to highlight here that there are several high-impact publications, some of which come from our group, on using metal organic frameworks for CO2 capture. So it isn't sort of a brand new idea. This is something that people have been trying to look into for quite a while. And so essentially what we're looking at is take CO2 from a flue gas and separate it out from that flue gas, and then eventually, which we don't look at, sequester that CO2 or utilize it. So what are some desirable properties of MOFs for this purpose? Well, they have a high surface area, they have high tunability, and there are many possible combinations of building units. So this is one of the most important properties for metal organic frameworks, for pretty much allowing us to use these for a lot of different applications. In fact, if you look in the literature, there's a lot more than just gas separation. And so this vast design space, we can highlight this just looking at the periodic table. 78 out of 118 elements have been used in the synthesis of these materials. And so you can imagine building all kinds of really interesting and exotic materials just using metal nodes and organic linkers. So yes, so MOFs are actually already being used for CO2 capture. So there is the first commercial CO2 capture system, which uses a MOF that we were involved in simulating this MOF called CAF20. And it's actually already being used. So it's being used to capture 1 ton of CO2 per day at a cement making plant. And it's been used for about 2 years. It's a pilot scale right now, but the process is currently being scaled to full size. And so what you see here is the structure of that MOF, or metal organic framework, and the individual building blocks. So cement flue, though, is 20% CO2. And as Donnie pointed out, we're interested in dilute CO2 capture. So this is a much more difficult problem because you have to have some sort of, the driving force now is going to be some sort of chemical interaction rather than or much more dependent on chemical interactions. And so, this, for several different reasons, becomes a much more challenging problem. And in natural gas combustion flues, we have 5% CO2. And so if we want to capture CO2 from natural gas combustion cycle processes, we need we still don't have a material that's viable for that yet. So can we use computational methods then to accelerate the design discovery of MOFs for low concentration CO2 capture? Well, yes. But before I talk about that, I want to point out how vast this design space is, and just like, I guess, talk about the number of combinations that we'd have to look at, how big this design space is. And so we have thousands of organic, inorganic linkers, thousands of organic linkers, and these can arrange not only in one kind of way, but you can arrange them in all kinds of other ways. And so this is known as a topology, so how those linkers are linked together. And so there are 3,000 known topologies. So if we just say, for example, that we can have one, we can take all the various combinations of this, that's already, and this is a pretty conservative estimate, that's already 10 to the 9 possible combinations. And so exploring this design space is going to be very challenging. And so what we can do then is, instead of looking at experimentally synthesized MOFs, we can look at hypothetically generated ones. So importantly, only about 100,000 MOFs have actually been synthesized. As I said, the number of the vastness of the design space is about 10 to the 9. And so this is actually a very tiny fraction of what is possible. So what we do is we build these MOFs in silico or using computational generation tools. And so we've developed some of those in the group. Here's a paper that if you're interested. And so we can generate these structures, and then we can investigate the properties using atomistic simulation and try and predict whether or not the material will be high performing. So what does our actual workflow look like? Well, what we can do is, as I pointed out, we can use atomistic simulation to determine the CO2 capture properties of any MOF, as long as we know the structure. And so typically this is done in a high throughput fashion using MOF databases. So we can take MOFs from experimental databases, we can build the MOFs, so we have lots of different possible MOFs we can look at. We then, this information of this crystal structure is stored in a file known as a CIF file, comprises a database, which then we can run our simulations on, both atomistic and process level, and then predict the carbon capture performance. And so I want to talk a little bit more about the simulations and what the bottlenecks are here. So it seems like a fairly simple process, but we have some pretty significant bottlenecks. So the first bottleneck that I want to talk about is these density functional theory calculations, or DFT calculations. So they take about 50 hours per MOF, 50 CPU hours per MOF. So that's pretty significant if you want to explore 10 to the 9 MOFs. And we also have 5 to 10 CPU hours per MOF in the other portion of our atomistic simulation, which is fitting charges and also doing some Monte Carlo simulations. So for this carefully curated database that we have of about 280,000 MOFs, and you can go here if you're interested in using that database, we've done this entire process for these 280,000 MOFs. That took thousands of CPU years in computing time, many different codes, and so we end up with this kind of complex and intensive workflow. On top of that, sometimes you don't need just one DFT calculation. If you're interested in other things, sometimes you need to do more. So geometry optimizations, for example, you might be interested in optimizing the geometry of the MOF using these accurate calculation methods like DFT. You'll need hundreds of DFT calculations. Thermal properties, 500 to 800 DFT calculations per structure. And depending on the system's complexity, you can actually the Monte Carlo simulations can become your bottleneck. So remember, those only were about 10% of the DFT calculation time. And if you want to look at water simulations, which will be important for CO2 capture in a real setting, you're going to be looking at 100 to 500 CPU hours per MOF. So the key point here is as we explore more complex properties of MOFs, the need for HPC can increase incredibly rapidly, specifically when we want to look at these more complex properties. So what we can do is we can use machine learning to try and solve this problem. So we can accelerate the search for these high-performing materials using many different techniques. And so what I'm going to show here are just a few different examples of what we're doing currently in the group. And so we have a postdoc in the group, Dr. Omin Kwan. He's working on a genetic algorithm in order to generate MOFs with good performance. So in essence, what this allows one to do is to explore that design space kind of in a more intelligent way, rather than just randomly building MOFs and testing their performance. Then we also have a machine learning project where a PhD student, Jun Lo, is working on predicting partial atomic charges of MOFs. And so this is important because what you might not, you don't necessarily need to realize is we needed to fit charges to these MOFs. And so how we did that was we needed a DFT calculation. So what we can do is we can just skip the DFT calculation if we want to just go straight to our adsorption simulations. And that cuts out quite a bit of compute time from the workflow. And something that I started working on is predicting binding sites within MOFs. And so this could be important for data-driven design or trying to extract some design principles of MOFs if we want to be able to just to start with a MOF structure, skip the DFT, skip the adsorption simulation, just determine, well, where will that CO2 go in the pore? Yes, and then finally, I just want to point out where we get all of our compute time. So through this collaboration, we've been able now to not only have access to, or not only utilize our own computing resources, so things at Compute Canada, our nationwide computing facility, and our own very small cluster at the University of Ottawa. But we've been able to take advantage of some of the other resources from Argonne National Lab and also Total Energies. And so with that, I'll pass off now to Dr. Chowdhury, who will talk a little bit more about the machine learning side of this problem.
Thank you, Jake. I will continue with the quest for increasing the problem complexity and then finding a convergence. As Jake kind of indicated that, the problem here is grows in exponential in size because it's one of the most difficult, challenging problem in terms of combinatorics. And, the Argonne team here listed, we are looking at the machine learning end and trying to put them in a scalable systems and trying to solve another very complex task. That is one of the challenging problems, and Jake kind of alluded to it, is that in dilute sources, in these large sets of data sets, only very tiny fraction of these MOFs are good at doing the carbon capture work. So this is one of those big design challenges that you can throw lots of data at it, but majority of your MOFs are not good at it, which is one of the biggest problem of, in movies they show that, oh, this is a super resolution movie from the cop camera and this blurred spot. I just super resolution it. Like, it's exactly that problem. Just super resolution on a needle in a haystack. So the question is, of course, how do you increase the size of the data set? The work done by these 4 graduate students, and 2 of them are mine, 2 of them are LU Huerta students, and a great collaboration with Tom Wu and with Donnie. So what we do is that we're bringing the codes that Argonne developed in terms of hyperparameter optimization, in terms of things that works on large-scale GPU systems, and eventually to Polaris, which is our intermediate system, and eventually to our exascale, which will need a little bit of, but all these codes have the pathway. So Deep Hyper is one of the highest performers, hyperparameter tuning code that we bring to the problem. And we can look at potential energy, we can use the 17 million data sets for the linkers, organic linkers that goes into the MOF that Jake talked about. We can also talk about properties of QM9 data set that is quantum mechanical calculation for 9 million organic linker. The question is, how can you use these things as a training set? That's what already people have pre-calculated these numbers and try to get to more physics-informed models, but in a very much machine learning friendly way. So one of the generative adversarial network model, the GAN that we are developing, we're constraining ourselves to a cubic GAN, so it's PCU GAN. So what we are doing is that we are dividing this whole thing up into just nodes and linkers and playing with those blocks itself, and dividing it up and then creating data structures so that you can run these things and compress the data structures, and you are not generating these tens of thousands of ZIP files, which our system administrators really hate. They really hate 100,000 ZIP files dumped in a day, right? So we are kind of compressing them and creating the topology, creating the nodes, and creating the combination through the encoder. Then we are using PORMake to make the new MOFs, and we're trying to increase the statistics. Then what happens is that we have this 10,000 epoch training number here, and A100s are really doing well, if you can see here. The numbers are really good, but how big a problem we're looking at here? Now we have 885 unique nodes. We have 6,764 unique linker that are good at this, and this size of the space is already 2 to the power 2.7 10 to the power 14 size number of MOFs than you generated using this. And this is much faster. In 2 minutes, we can generate 10,000 MOFs, which is much faster than other methods. So this is, I will not get into the workflows in terms of neural networks, our encoder, our regressor model, then CO2 load prediction. But then, we also have a topological data predictor, which we look at, it's the same problem, is slightly different using topological data and topology perspective for different MOFs. And, then, Jake and others are producing electronic structure data with electron density, electrostatic potentials at a very rapid rate. So they are also increasing our data size. So we can also throw this into our model and say that, hey, we're not putting exact quantum mechanics, but can we introduce these charge densities into these crystal frameworks? And can we learn something which is not, we'll ask the physics question later, but is there a correlation in this data, in the electronic structure for this high performance one? And can we learn from them and generate more MOF that are better at carbon capture, right? So it's a kind of discovery process. So we are using this topological data analysis where you get higher dimensional data sets like electronic structure data. You can really screen through it, and we can then put 100,000 MOFs. I'm not reading the detail because we have lack of time, but essentially it does the data compression. you can sort of store 12,000 MOFs in a 10 megabytes file, which like compresses the problem, and then you throw it at your performance goes up tremendously. So that is important because this is a large-scale data problem, large-scale compute problem of really massive kind, and it's a search and design problem, and then multi-objective optimization problem. Eventually, Donnie will ask us that what is the cost of all these MOFs, how much they cost. So then, then what we do is that we have this B1 norm, and we have the B2 norm. What are these is a multidimensional simplexes where you have connecting these data points. What is a B1? If you look at the structure, it is actually a pore. So you're kind of forming a pore, like the way Jake showed, and B2 is the volume of the cavity, because it's the next dimension. Don't ask me what is the fourth and fifth and 10th dimension of this data. My graduate student can keep going on about it, but I stop at second and third dimension, right, in terms of my thinking. One is a pore through which it goes, and the other is a volume in which the carbon dioxide will stay absorbed. So we can see features in these data sets, in this kind of analysis that is very high throughput and high screening rate of 100,000 MOFs we can do very fast. And we find regions of features in spaces where the best performing metal organic frameworks that are good at carbon capture shows up. Don't ask me why yet, because we'll go back, extract them, and answer the why later. Because our method is to go through all this generative state, increase the size of the data, reduce the size, and generate the ones that are good at it, right? So, when I asked what these MOFs are, what are the commonalities, you look at 9 to 11 angstrom pore size, seems to be very good at it. Don't ask me why. And these are the kind of volume of 10 angstrom cubed sphere in which carbon dioxides are happy to reside. That's what our data is showing from the electronic structure data, right? So, these are the features that we were going to explore, and we're going to publish the exact why answer to that. So, how is our workflow? This is my last slide. So, we are kind of looking at AI for steering this infinitely large multi-objective space, because you are now walking into this massive space with the power of supercomputing, power of GPU nodes, and eventually our exascale systems. And you start with exascale MOP, you use mold simplify, you split out the linkers, metal nodes, and topologies, you use the generative models, you randomize initial state, have the linkers, metal nodes, topology, you use PoreMake, very good at making new MOFs, and then you make generative MOF structure, trained regressive prediction, and adsorption simulations. You kind of go like that. And the good part is that these linkers, we also use a diffusion model, which is a new methods of generative methods. The diffusion models are really good at sort of modifying the electronic structure a little bit from that large databases, so that if you found some MOF that has the features, can you improve even the physics of one of the linkers and change the functional groups and tweak around the binding site to get it even better, right? So the question is that our options are really all these tools to work together towards problem and sort of converge into a solution. So, of course, we're looking towards exascale, and we have the National AI Test Bed with wafer-scale computers like Cerebrus, the Sambanovas, and others. So at Argonne, we can test different algorithms in different machines so that we know that this problem is going to get larger and larger, and interest is going to grow. So we really appreciate DOE funding and this collaboration. Thank you so much.